All right, so here's the start of assignment 3.3. Um, we'll see how far we get before I have to stop the video, and then I will pick it up with another video. So make sure you title it, name, date, and so on. So I know it's you doing the work. And we're going to do our work together. And then you're going to take a picture of it, you're going to upload it, and so on. So let's start. So this lesson, assignment 3.3, was on the chain rule, sometimes called the general power rule, and that's what we're going to practice. So this is one of those shortcuts that was new. So we knew the product rule and the quotient rule, but this is a new shortcut called the chain rule that we're practicing. So let's do it together. So y equals 3x plus 5 cubed. What would the derivative be? So do the correct notation. So for the chain rule, we look at the outside and then times the inside. So we perform the power rule on the outside. So 3 times 1 in front. Write the base as you see it. Subtract 1 from the exponent. That's just the power rule. Times. Now, if the base, if there's a derivative there that's not 1, then that needs to be included as a product at the end of the shortcut. So the derivative of the base is 3, and you just did what's called the chain rule. Now, you could also write this as 3 times 3, that's 9, and you could simplify it a bit, which could be a good skill to have if you needed to apply it in some way. All right, number 2, f at x equals 3 times 7x plus 5 to the exponent 4. So use correct notation for derivative. That's f prime at x. So the chain rule, we're going to go 4 times 3, that's 12. 7x plus 5, subtract 1 to the exponent. Then the derivative of the base, which is 7, and that's done. Now, of course, you could go 12 times 7 and write that answer as 84 if you wish. Number 3. Now for number 3, in order to do the chain rule, in order to do derivative shortcuts, we have to write it calculus friendly. So when I see a radical sign, or if I see a fraction with a variable in it, I want to write it as a power exponent. So for this one, right away, I'm going to write it as 2 subtract 3x to the exponent 1/2. That way, I can then take the derivative shortcut here. So 1/2 times 1 in front, subtract 1. Remember, 1 take away 2 is negative 1/2 times the derivative of the base. Now, the derivative of 2 is 0, but the derivative of negative 3x is negative 3. So it is important that the sign is correct. You could also write that as negative 3/2. And you could also write that as a fraction because of the negative exponent, and you could write it as a square root in the denominator to the 1/2, but that is pretty the way it is. Number 4. Again, when I look at this, the first thing I look at is I don't want to take the derivative of a fraction if I can help it. I want to write it as a power. So I'm going to write this as, do you know how to write that without a fraction? 1 subtract t to the negative 2. Then I'm going to take the derivative. So negative 2 times 1 is negative 2. Subtract 1 from the exponent, and it's now negative 3. And then what's the derivative of the base? So the derivative of 1 is 0, and the derivative of negative t is negative 1. Now, negative 2 times negative 1, that's positive 2. And it's 1 subtract t to the negative 3. 5. So again, the first thing I notice for number 5 is I want to write that calculus friendly in a way that there's no radical signs and no fractions. So for number 5, to write that, I'm going to use parentheses. Inside, underneath the radical is x squared plus 1. And then what exponent could I write that as? Well, the power inside the radical is the numerator, and the root is the denominator. So now it's calculus friendly. So now we can apply the chain rule. 2/3 times 1 in front is 2/3. Subtract 1. So 2 subtract 3 is negative 1/3. And then times, this is sometimes this is called the hook, the chain or the hook that you can't forget at the end, the derivative of the base. So that's 2x. The derivative of 1 is 0, so I don't need it. Done. Now I could also write this as 2 times 2, which is 4x over 3, and I'm happy leaving it as to the exponent negative a third. Though you could write it as a fraction if you had to. As a fraction, 4x would be in the numerator, 3 in the denominator, and 1/3, that negative 1/3, the negative means it's reciprocal, so it's in the denominator, and the 1/3 means cube root, so it's the cube root of x squared plus 1. You do need to have that skill to be able to go from an exponent to radical to a fraction and understand that they are equivalent, and you use the form that is the simplest that you need to use. All right, number 6. For number 6 again, I'm looking to see if there's any way I can rewrite it first to make it simpler for the shortcut. There is not. The next thing I look at is when I see x times this is far different than a constant, like a 3 or a 4 or 5. So when I see a variable and it goes x times, that means I have to do the product rule. And when it comes to that, I also have to do the chain rule. So it's actually 2 rules here that I need to follow. So the first is x, and the second is 2x plus 3 to the cube. So we're going to do the product rule first. So first and second. So the product rule is the first times the derivative of the second. So 3 times 1 in front is 3. 2x plus 3. Subtract 1 from the exponent. And then we need the hook or the chain. So the derivative of the base is 2. So all we've done so far is the first times the derivative of the second, plus the second, which is 2x plus 3 cubed, times the derivative of the first. Now the derivative of x is just 1, so I don't need it, but I'm going to write it down so you can actually see the product rule and how we had to use the chain rule within the product rule. Number 7. Is there a better way I can write number 7? So let's look at it. Yes. I wonder if you can try. What's a better way we can write this so we can apply the shortcuts to take derivatives? So I'm going to write it as x plus 1. Remember, don't get frustrated. You could also press pause and try. X plus 1. Now what would the exponent be? So it's going to be a negative exponent because I need to do the reciprocal, so we don't have a fraction. And square root means 1/2. So it's negative 1/2. Were you able to do that on your own? I think you did. Then the derivative is the chain rule. So negative 1/2 times 1, subtract 1 from the exponent. So negative 1 subtract 2 is negative 3/2. Then, if I look carefully, is there a chain here? Well, the derivative of x is 1, and the derivative of 1 is 0. So do I need to go times 1 for the hook? Does it change anything? And the answer is no. So I don't need that 1 there. So I need to include that when the derivative of the base is a number other than 1. Number 8. In number 8, is there any way I can write this in a better way? So when I look at it, can I use negative exponents? Can I simplify it and so on? It's not going to help. To me, the product or quotient rule are equally whatever. So there is no way to factor or simplify it and write it in a simpler way to use. There is no chain rule here. Instead, I have to use the quotient rule. So there's no factoring or simplifying here. And I just got to remember the quotient rule. So nice long fraction line. And what is the quotient rule for number 8? So that's the bottom times the derivative of the top. Subtract the top times the derivative of the bottom. And it's good practice to know this. The derivative of the bottom is 1, so I don't need it. Times 1 doesn't change anything. And then take what's in the denominator and square it. And unless it tells you to simplify it, you are done. And you are. Number 9. Let's do some applications here. 9 says find an equation of a line. That is x, y, and equals. So as soon as I see that, I'm going to set up a little template to help support that to make it simpler. In number 9, it tells me the x coordinate is -1, the y coordinate is 2. How would I find the slope of that tangent line? And that's the derivative. And it's not just the derivative, it's the derivative at the x-coordinate. That's what I need to find, and then I can write my equation of line. So underneath, I'm going to first just do the derivative of what I see. So for number 9, let's just rewrite the function so I see it again. So I'm given the square root of 2x squared plus 2. So I'm going to write that as 2x squared plus 2 to the 1/2. Then I can do the derivative shortcuts. It's 1/2 2x squared plus 2. Subtract 1. That's 1 take away 2. That's negative 1/2. Then do we have a hook or a chain? So the derivative of the base, 2 times 2, that's 4x. So there is the derivative. Now, in order to find the slope, wherever there's a 1, I'm going to plug in 1 to find the slope. So we have 1. When I plug 1 into here, 1 squared is 1, and 1 times 2 is 2, and 2 plus 2 is all 4, and then 4 times 1 is 4. So let's continue to see, do you have the skill to simplify this? So we have 1/2. The 1/2 means square root, so the square root of 4 is 2, and the negative exponent means reciprocal. So the square root of 4 is 2, reciprocal means that's 1/2, not a negative answer. And then I have to be able to multiply this. So 1/2 times 1/2 is a quarter, and a quarter times 4, that slope for number 9 is simply 1. Oh, did I plug in the wrong number? So, is it positive 1 or negative 1 that you plug in? Now, when you plug in negative 1 and you square it, same thing, but this 4 is actually should be a negative 4. So let's make that quick adjustment. That should have been a negative 4. So what does that mean? That slope then is a negative 1. Now we're going to put it all together. So how do you write the equation of a line when you know the slope and the x and y coordinate? So the slope is negative 1. Now we're going to change the sign. So it's x plus 1. And then keep the sign, plus 2. That's it. That is a perfect equation of line. If I needed to, if it was multiple choice, I could go negative 1 times x, which is negative x. Negative 1 times 1 is negative 1, plus 2, so that's plus 1. So you could also write it as negative x plus 1. 10. Same thing, equation of a tangent line. So I'm going to write down x equals y equals, and m, the slope equals. So in number 10, you're given a point, so you know the x and y coordinate right away. To find the slope, it's the derivative at 2. You're given an equation that I need to take the derivative of. Now, for this one, again, I noticed first is that there's a monomial in the denominator. That means there's a term. It's not a binomial, trinomial, and it's something I can simplify. So that x in the denominator belongs to the x and to the 4. So do you see how I separated into 2? So this answer would be 1, x divided by x is 1. And the second one would be 4x to the negative 1. Now it's calculus friendly. So if I take the derivative of this, the derivative of 1 is 0. The derivative of this, negative 1 times 4, is negative 4. And subtract 1 to the exponent. So now this is far simpler to take the derivative and then plug in positive 2 to find the slope when x is 2. So we have a negative 4. And then what does this mean? 2 to the negative 2. Well, 2 squared is 4. The negative exponent means reciprocal. So the reciprocal of 4 is a quarter. When I go negative 4 times a quarter, that just simplifies to negative 1. So now put it all together and you have y equals negative 1. That's the slope. Change the sign. X subtract 2. Keep the sign. Plus 3. Done. All right, number 11. It says find the indicated derivative. So d by dx of 2x subtract 3 to the 4. So that's just a notation, a different notation to show derivative. So just take the derivative of this. So 4 times 1 in front. Subtract 1 to the exponent, and then the derivative of 2x subtract 3 is 2. That's called the hook, or the chain. That's it. You could go 2 times 4 and make it 8 if you want to. 12. the derivative. Now you're taking the second derivative, what you're asked for, but I can't take the second derivative without taking the first derivative first. So I'm first going to take the first derivative. That's the notation for the first derivative. 3 halves times 1 in front is 3 halves. Write the base, subtract 1. So 3 take away 2 is positive a half. And now the hook, or the chain, which is 2t. Now, to this, I am going to multiply the back and the front to simplify it so that the next derivative is easier to do. So there's a reason to do this. So when I go 3 over 2 times 2, the 2's divide out, and all you're left with is 3t. And then you have t squared subtract 1 to the 1/2. All right, now I can do what it's asked to do. So again, I'm going to find the second derivative. Make sure my notation's correct. So this is what I'm asked to do. Notice I write down the original, what it looks like. Though, in order to find this, what it's asking for, I'm actually just going to take the derivative of the first derivative. So it's important, AP exam as well, that you do the notation correctly. So the second derivative is equal to the first derivative of the first derivative. So these are equivalent to each other. Now let's answer it. So I have 3t, and I have t squared subtract 1 to the 1/2. So this is going to involve the product rule. So we don't have a constant in front, but an actual algebraic expression in front. So this is going to involve two things. So this is the first and the second. So I'm going to do the product rule, and then within that, I'll have a chain that I'll have to do. So what's the product rule again when you're multiplying? So that's the first, which is 3t, times the derivative of the second. So that's 1/2 t squared minus 1, subtract 1, that's negative a half, and then the hook, which is 2t. So the first times the derivative of the second, plus the second, which is t squared minus 1 to the 1/2, times the derivative of the first, which is 3. Done. You could simplify that, but there's no need because there's no extra steps after it. So that's a good answer at the end. Number 13. In number 13, it says, find the points at which the line tangent to that graph is parallel to that. And you may use a calculator. All right, so I will if they say I may. So what does that mean? Find the points. So first of all, tangent means derivative. So step one is to find the derivative of what I'm looking for. So the derivative of that function is 3 times 1 in front, which is 3. Subtract 1 to the exponent, and then there's the hook. So the derivative of the base is 2. I am going to simplify it more because we're in the middle of the question at the end. So 2 times 3 is 6. And now that's a little bit easier to work with. Then it says, I need it to be parallel to a line. Now, parallel means the same slope. So we have the slope of the tangent and another slope, and we need to make them equal to each other and then solve for x. So what's the slope of the line that's given? And the answer is, it's 24, right? That's what m equals. So now we have an equation to solve in terms of it. Now, for number 13, it says you can use a calculator if you wish. I don't see any need at this point to use a calculator, but maybe I will. So you could use it to solve it. Divide by 6. I don't see an irrational answer here, or might be, because when I divide, I get 4. And then when I take the square root, it's going to be positive or negative because I'm solving a quadratic, but the square root of 4 is rational. So I can get two nice answers out of this. So I have positive or negative 2. So I have two situations here, one for positive 2 and one for negative 2. So for positive 2, I'm going to add 3 to positive 2 and get 5 and then divide. For the second possibility, I'm going to add 3 to negative 2. So negative 2 plus 3 is positive 1. Oops. And then divide by 2 and you get 1/2. So I get two x coordinates. One is 5 over 2 and the other one is 1 over 2. So it asks for the points. So I still need to find the y coordinate that goes with it. So if I go back to the function f of x and plug in what would I get? So first of all, I want to plug in 5 over 2. So if I plug in 5 over 2, it would be 2 times 5 over 2. Subtract 3 cubed. So let's see what that gives me. So the 2's divide out. 5 take away 3 is 2, and 2 cubed is 8. So we got 5 over 2 and 8. If I do 1/2, so here's 1/2. 2 times 1/2 take away 3 cubed. So 2 times 1/2 is 1. 1 take away 3 is -2. Now that matters because when you have an odd exponent, -2 cubed is not +8 but -8. So at what 2 points do you have a slope of a tangent line that's parallel to that? And the answer is 5/2 8 and 1/2 and -8. All right, number 14. G at x equals, parentheses, 5x, close it, cubed, and then it gives you information about it. So f at 1 equals 2, the derivative at 1 equals 4, and I'm asked to find the derivative at 1. So step 1 is to find the derivative of what I'm looking at. So this is given conceptually, and how would you do the rule generically without an actual function being given there? So the chain rule is 3 times 1 in front. That's easy enough. Subtract 1 to the exponent, that's 2, times the derivative of the base. Well, the derivative of f at x is just f prime at x. So that part there is called the hook. Next, it asks you to find the derivative at 1. What does that mean? Everywhere where there's an x, put in a 1. Then, using the information given, f at 1 is 2. So that's 2 squared times the derivative at 1 is 4, and then just complete it. So 4 times 3 is 12. 12 times 4 is 48, and you have your answer. Number 15. Turn the page. So f at 2 equals 3. G at 2 equals 2. F prime at 2 equals -1. G prime at 2 equals 4. And then lastly, G prime at 3 equals 5. All right. So that's given information before we do the work it's asked us to do. So find the derivative with respect to x of G f at x. So first of all, what would that look like? And it says at x equals 2. So what would the derivative of this look like? So this is called the chain rule again. And in this sense, because we don't have a base and an exponent, what you're thinking through this generic case, this is a composite function. It's the derivative of the outside times the derivative of the inside. So the chain rule in this case is the derivative of the outside times the derivative of the inside. So the derivative of the outside times the derivative of the inside. So we're going to, wherever there's a x, we're going to put in 2. And then we're just going to keep going from there. So we have the derivative. Now f at 2 is 3. The derivative at 2 for f is -1. And then one more time, g, the derivative of g at 3, right here, is 5. And that's it. And then you're done. So 5 times -1, and you get the answer -5. Another one like that. So this time you're given g at x. Even though it doesn't look it, it's should be a dot there, right? To really make sure you understand what's happening here. G at x times f at x. So if you really saw the dot, what would you do? And what rule would you follow? So this one is called the chain rule. What rule is this one to take the derivative? When you see that times, it's called the product rule. So what is it, generically speaking? So it's the first, g at x, times the derivative of the second, plus the second times the derivative of the first. So there's the product rule generically. Then it says at which value? At x equals 2 again. So at x equals 2, wherever you see an x, put in 2, and then we're just going to follow with the information that we have and then get our answer. So g at 2 is equal to 2. F prime at 2 is equal to negative 1. It's all given in the question. F at 2 is equal to 3. And what's left? Oh, I put an x here. This should have been just a 2. G prime at 2 is 4. So we have negative 2 plus 12, so that answer is 10. Number 16. So in number 16 it says find an equation of a line tangent. So equation of a line tangent means, here's my template, x equals y equals m equals. And it says to the graph y equals 3 to the x when x equals, and you'll need a calculator. So I'm going to use it. So x is 1.2. The y coordinate would be 3 to the exponent 1.2. So I'll need a calculator for that one. Let me do that. So 3 to the exponent 1.2. 3 decimals, so 3.737. And then how do I find the derivative at a point? So I'm going to show you where that is again. So I'm going to press menu. I'm going to go to calculus, derivative at a point. So x is our variable. The value, oops, I just need to move the cursor, not enter yet. The value is when x is what, 1.2. Now you can press enter and then just type in the function, which is 3 to the x. Control enter, again, 3 decimal places, so it's 4.10. It's okay to truncate. You don't have to round. 105. And then how would you put that together as an equation of a line? You go y equals 4.105. You'd say change the sign, x subtract 1.2, and then keep the sign plus 3.737. Done. Number 17. All right, so in this question, this is now review and some calculus questions to make you think, rather than specifically about the lesson that you did. So we're not now thinking chain rule and derivative rules and tangent lines. It could be anything. So I'm not going to have you rewrite the chart or anything in your work and so on. We're just going to answer it. But I'm going to put the chart up here. So a sprinter in a 100-meter dash is clocked every 10 meters as shown in the table. So that table, it is continuous. It's just that every 10 seconds data is recorded, even though there would be meter 1, meter 2, meter 3, and so on. So to understand what table that you're looking at, so we start at 0. In 10 meters, it's 1.4 seconds. Then at 20 meters, to get to there, it took 2.5 seconds. And you can see everyone until we get to 100 meters. At the end, the entire time it took to get to 100 meters is 10.2. So that's a more practical situation of someone sprinting than thinking it's the same speed all the way through. So you accelerate, you might slow down and then accelerate again. It's fluid, right? So it's not a linear situation when someone is sprinting. At times they are running a little faster and a little bit slower and so on. All right, so let's answer the question. How long does it take the sprinter to finish the race? I think I answered that one for you. So the answer is 10.2 seconds, right? Looking off the chart. B, what is the sprinter's average speed? In this case, velocity and speed would be the same thing because they are sprinting in the same direction. If they change direction, then you could think about velocity. In this case, velocity and speed mean the same thing because it's positive the entire way through because you're only going in one direction. All right, what is the sprinter's average speed? Well, how do you find average speed? And you might remember this little formula from algebra, the average speed is used where distance is equal to rate times time. If you got rate by itself, that's speed, you would divide, right? So it's the change in distance over the change in time. That's what gives you average speed. That little cute little triangle is a change symbol. So how much distance was covered from 0 to 100, right? So the change in distance was 100 meters. What time? 10.2 seconds. And that's your answer. And then you could divide, and you can use your calculator if you want. So it's 100. Oh, for the first 50 meters. So be a good reader, right? So the distance is 50. How long did it take to get to 50 meters? 5.4. So that's what you divide in your calculator. And units are important here. They need to be there. They're not just whatever. They have to be there. And so if you divide, the average speed over the first to 3 decimal places would be 9.259. So you just divide that in your calculator, and that's meters per second. Absolutely necessary. C, what's the sprinter's speed between 20 and 30 meters? So between 20 and 30 meters, how many meters are covered? So between 20 and 30, that's 10 meters. How much time took place? So if you like, you can set this up as, why do I do that? Set this up as a slope formula. So if you set this up as a slope formula, you'd have 2 points. So from 20 to 30, it'd be like going 30 take away 20. That's where 10 comes from. And time would be 3.5 take away 2.5. So units are important. So what we have is 10 meters over 10 seconds. And so, right? 10 meters over 10 seconds, right? Oh, sorry, over the second one. I'm getting crazy here. So a few things I did wrong here. So, first thing, I was entering D. That's silly. Next, when I subtract it, it's not 10, but 1 in the denominator. That'd be nice to be able to do simple. And then when you do it, that's 10 meters per second. All right, let's see if I can get back on track here. C, skipping C. Spinner speed over the second 50 meters. So for the second 50 meters, they covered 50 meters. And then the second 50, you would go 10.2, subtract 5.4. That's how much time it took. So 10.2, subtract 5.4, that's 4.8. And then divide that in your calculator. 50 divided by 4.8, that's 10 point, again, you can truncate, 416. So if I compare this to the first 50, was he going faster in the first 50 or the last 50? So you can tell that these sprinters, they go as fast as they can, but they are going to slow down, I think, a little bit as they do the second 50. I did D. E. What is the sprinter's average speed between 30 and 40 meters? So between 30 and 40, that's 10 meters. The time that is passed between 30 is 4.5 and 3.5. So I won't make the same mistake. That's 1. So that's 10 meters per second. So between 20 and 30 and 30 and 40, notice that the acceleration is constant. There is no acceleration. So the velocity is constant. The speed is constant. So they're going the same speed. F. What is the sprinter's approximate speed as he passes the 30-meter mark? So this is now a different way of asking for what's the instantaneous speed, not average, but as they're passing this one, what would the speed be? So for that, I need to understand that if you take, and you want to estimate it, what's happening around 30, look at what's around it and find the slope between those 2 points. So again, it's distance over time. So 40 take away 20 is 20. And then the time, 4.5 take away 2.5, that's 2. And this makes sense, right? So as they are passing, this person's passing the 30-meter mark, the approximate speed it's going is 10 meters per second, which totally makes sense. Because we said the speed for the first 20 and so on, that it was that 10, 10, and now 10 again. But we use the points that are around it to approximate it. G. It says, during which 10-meter segment is the sprinter running the fastest? So running the fastest would be taking each one and seeing which would give you the greatest answer. Now, we're going to use some math and thinking here to not do each one. So we're looking at each segment and going distance over time. Now, the top table here, it doesn't change. Like the distance, it's 10, 10, 10, 10, 10, 10, 10, all the way across. So I'm not going to just do each segment and then do 10 of them and see which one is the biggest number. I'm going to think, and the thinking is this, that if which segment is going the fastest would be when the time is the quickest, meaning the least amount of time would give you the most amount of speed. So for 10 meters, what gave you the least amount of time to cover 10 meters? That would be the fastest. So 9.3 and 10.2. So that's 0.9 seconds. So I'm going to keep looking and see if there's a number that's smaller than 0.9. So 8.5 and 9.3, that's 0.8. So that one's done. So now I got 0.8. 7.6 and 8.5, that's 0.9, not faster. This is 1 here. This is 1.2. This is 0.9. Here is 1. Here is 1. Here, again, is 0.9. I'm just subtracting. And then 1.4 subtracting. So which one gave me the least amount of time in terms of that? So you can see between 80 and 90 is your fastest interval time. So between 80 meters and 90 meters is the fastest 10-meter interval. Why? Because it took the least amount of time to cover the 10 meters. And that's what makes it the fastest. All right, last one in this group, H. During which portion of the race is the sprinter accelerating the fastest? So for that one, we're looking at the slopes of the slopes. So if I'm looking for acceleration, for instance, remember we talked about 20 to 30 and 30 to 40? So what is the speed or the slope? So the speed is 10 meters per second, and then it stayed 10 meters per second. So where is he accelerating the fastest? Well, right there would be the least because it's constant. So there's no change. So the acceleration is 0 from 10 to 10. So I'm looking for the big change. So you think, where's the biggest change? What 10-meter one where you would be going from one to the other, the number changed the most, the greater number? Are you thinking? All right, so we're going to now answer it. You ready? So right at the beginning, how fast is he going? Or she? 0, right? And then, how fast we end up going is when we do the subtract dividing. It's 10 divided by 1.4. How fast is that? That's 7.14, 2 or 3. But the whole point is that all these others will be somewhere between 7 and 10 or 11 meters per second. So where does the greatest change happen? And the answer is at the beginning. So the greatest acceleration is when you go from 0 to 7. There's no other change that is as great as that. So from 0 to 10 meters is the greatest acceleration. All right, number 18. A particle is moving vertically on the y-axis with that position. So here's a position equation. So this is a question from 3.1. So whenever we do an assignment, there will always be questions that will continue review and review and review so that you don't forget and just learn the new thing and forget the old thing. We don't want that. So 1/3 t cubed plus t squared subtract 3t plus 7. So that's the position of it on the y-axis, and it's moving up and it's moving down. Okay, when is the particle moving upward? And don't use a calculator. So to figure that out, we are going to find the velocity, because the velocity tells me direction. And if it's moving vertical, positive means it's going up, negative means it's going down. So let's take the derivative here. 3 times the third, that's 1. So it's t squared. So 3 times 1/3 is 1, and then subtract 1 from the exponent. 2 times 1 is 2, subtract 1 from the exponent. Negative 3t is negative 3, and the derivative of 7 is 0. Next, we're going to make that equal to 0, because we want to know when the particle is at rest to then have intervals to know what direction. Because if it changes direction, it has to rest for a moment. All right, to solve this, we're going to factor. That's plus 3 and minus 1. We're going to solve it. So the first factor gives you the answer negative 3. And the second one, positive 1. Remember, it's conceptual, not a real-world situation, so time t can be negative. We're going to draw a number line. So this number line is just for the velocity of the particle. And on there, we're going to label negative 3 and positive 1. And this goes from negative infinity to positive infinity. And we're going to plug in numbers into the velocity and see if the answer is positive or negative. So pick any number smaller than negative 3. So if I pick negative 4, what do I get? So negative 4 plus 3, negative 4 take away 1. That's a negative times a negative. So what direction is the particle moving from negative infinity to negative 3? Up. I'll even write that in. Up. Pick a number between negative 3 and 1. 0. So plug in 0. Any number works, but 0 I think is the easiest. A positive times a negative. So what's happening here? It's moving down. Plug in any number greater than 1. 2, 3, doesn't matter. So I plug in 2 and I get a positive times a positive. So the question is, when is this particle moving down? What interval? So can you see from negative 3 to 1, the particle is moving down. And notice I use parentheses around it because negative 3 and 1, the particle is technically at rest. Yes, camera. Okay, you can now. You want me to help you get an apple? Yeah. Okay. All right, I'll be right back. I'll get an apple from my daughter, and then I'll be back and finish off the assignment.